So one of the problems that we identified is that we haven't really been thinking about negation in two-way rule models so far. But it seems as though for resolution theorem proving that negation plays some important role.
Well, that's the point. I mean, and look, there's this interpretation. Okay, so I was thinking about this also. You know, the fact that we are claiming all of mathematics is represented by two-way equivalences is kind of like, well, whatever. You know, that's a possible thing. You could also say all of mathematics is represented just by single expressions, right? That's essentially what I did in NKS, right? And the question is, what rules of entailment do you use? Right? So in NKS, all I was doing was what I was doing was to say something which I don't think is really ultimately that supportable for mathematics. I mean, I think this idea that mathematics has these things which are kind of, you know, where there's a bucket of truth, so to speak, at a given stage in mathematical history. That's a better model for mathematics than to say there's a fixed set of axioms. And then here, maybe I can make some notes here. Let's do you want to let me share for a minute? And then you can, is the notebook that you were just showing, is that in the Dropbox?
Yeah, that's the function repository function.
Oh.
That's turned into exploratory working notebook. The two-way multi-replace. Okay,
I think that, you know, let me make a suggestion that we do have this whole section here of these mathematics notebooks, and I think maybe we should just add these to that. Okay, so in a sense, let's see, we were in here. Well, do you want to just put that as mathematics 12, and then I can do mathematics 13 after that?
Yeah, sure.
Do you want to
it's just gonna have like a template of a function.
Well, why don't you just copy out the part that isn't that, just so that we don't get totally confused.
Okay, I can also. So this is a
mathematics 12, and you might say mathematics dash NM or whatever, dash 12 dash NM or Nick or whatever you want to say. Okay, just so we don't get...
I'm just confused. There's like we already had mathematics folder in the general research, and this is
no. This is in the 2021 physics project stuff.
Okay. Working material. Yeah, found it.
So Stephen, you were saying
general minimal models for mathematics. Okay. You know, type 1, axioms are fixed and things are being derived. In other words, that is the thing where the axioms are and type 2 is you know, propositions, axioms plus propositions are progressively being added.
Right.
So in type 2, the axioms have to be sort of represented the same way as the rules.
So in type 1, all is entailment for type 1.
Type 1 is very similar to this is like the usual formulation of the physics project.
Okay, but for
right, because it's got a rule which is not of the same type. It's got a rule that says left-hand side goes to right-hand side, whereas the in other words, the rule doesn't operate on a thing of itself, so to speak. Right? The rule is something like, x, y, y, z goes to, x, x, y, z, y, w or something, right?
Yeah.
Right. Whereas, but that rule is operating on something of the form, whatever it is, it's just a plain list, right? So this is code is not equal to data, so to speak.
Now, just for clarification, so this describing these as minimal models for mathematics, but part of this study is that we begin with this, sea of possible statements that may or may not belong to mathematics. So, and we describe
the same. That's a slightly different model.
No, I know. We describe that as the meta mathematical model. So I just want to.
Well, I think this is the meta. This is all.
Oh, okay.
This is all meta mathematics.
Well, then the question is, you see, so if we're beginning with this repository of possible statements,
no, that's not what we're doing in type 1. In type 1,
right. Okay.
The initial conditions.
Yeah.
In type 1, okay. Let's see. Type 1 results are paths. Okay, so the data in type 1, data is typically expressions.
But does this mean that? Oh, yeah, no, go ahead.
No, wait a second. Maybe also. Yeah. Data. Okay, 2 cases. Case 1, data is expressions, and theorems are paths. Well, proofs. I mean, theorems are connected pairs of expressions. Okay, that's the NKS version.
Okay.
Theorem proofs, because theorems themselves also an expression. But the proof is
no. See, that's not true in this case, because here the data is just an expression. Well, that's a different case. That's case 2, I think. Case 2 here is the theorems, the data is theorems, which are also expressions. And okay, and then here, it's like we're deriving. So then this is the case where the, quotes law of entailment.
Yes.
Is application of an axiom.
Right.
Which isn't quite the same. Is that the same as substitution? I don't think so. Is that like, I think that is like, wait a minute, that is like substitution. Okay, that's substitution, that's raw substitution into an expression. Okay, so this, in this case, the data is theorems. And so then what we're deriving is, with this axiom, this theorem turns into this other theorem.
Okay.
Right?
So this is like the constructivist version, where the only thing we have are data we've actually kind of built. Yes?
Yeah, that's right.
Sense.
That's right. But so here, what we've got is, the only way to build is with raw axioms. Okay, which is super inefficient,
Okay.
But this is very inefficient compared to lemmas.
Okay.
But it will work. Okay, so let's understand actually, will it work? Will it work? What do we start from? Okay, so here, initial conditions, in this case, Here, initial conditions are whatever expressions we want. And we are forming connected graphs of things equal to them, right?
So does case one, type one, permit, alternative mathematical systems?
Well, yeah, you can
Yeah.
look, in type one, the fundamental input is axioms.
Mm-hmm. Okay, so
And that's like the rule, that's like the physics rules. Okay.
Okay.
So is it like case one is more like metamath, and case two is like any other functional, just by carry forward type theory stuff?
Maybe so. Let's understand that. Okay.
Mm-hmm.
But let's keep going here. So look, the only way to build is with raw axioms. But now, what is the initial condition in this case? The initial condition, okay, here, the initial condition must be true. Must be something representing true.
Right. An initial object, categorically speaking, right?
Yeah, I guess so.
Anything constructible.
Anything I mean, that's the idea. The initial object, at least in the constructivist sense, it's just right.
Okay, so
wait, the initial condition, the ticket for admission, so to speak, is that it has to be constructed, and so true is the ticket of admission into this case two.
What do you mean constructive? It's just a symbolic expression. It sits there.
Well,
it's meaning. Look, to make quotes meaningful math, the initial condition should be something quotes meaningful.
Yeah, and that's what type theory models, right? It's meaningful, meaning that type is inherent. What do you
mean? Inhabited.
The word inhabited, right?
Right, which means it's true.
Yeah.
Right. It's true. It can be proved. So it's constructible.
Data is theorems is just a bunch of types that you have, but if the type is true only when it's inhabited.
Right, and if it's inhabited, it has a constructor, because those are.
Okay, hold on. Let's be explicit here. I mean, in this case, you have raw axioms, and the entailment is substitution using the axioms. Right, so this is a very traditional multi-way system, if I'm not mistaken. I think the axioms, okay, so in this case, axioms are of the form, LHS, a pattern goes to RHS, right? If I'm not mistaken. Yeah, that's what we mean by this case. And the entailment is just you apply that rule. You keep applying that rule. And, the thing I looked at in NKS. See, look.
It's not necessarily a rule, right? Axiom, we don't restrict it to just two rules here. It can be just an expression. Right?
No, I don't know how to apply an expression. That's the point. That's the point of type 1 as opposed to type 2.
But this is type 1 still.
This is type 1 here.
It has expression and rules, and we are comparing it like to types. It's like functions and just terms. Right?
Okay, let me understand.
An axiom.
I don't quite understand that. But I'm just trying to work through my understanding here. So this is the first NKS version. If we remember what I did in NKS, and then we're going to get to negation here. Okay.
Okay.
What I did in NKS was my first kind of model was just this. Okay, you got fixed axioms, you apply the axioms, this is a proof.
Yep.
See what I'm saying? Okay, that was case 1. Okay, the second thing was
that's case one. Okay. Yes. I see.
this is okay. Let's illustrate this. This is okay. Let me just make this
Yeah,
picture.
I was going to suggest that. Yeah, that'll be helpful.
Right. This is case one. This is type one, case one.
Okay.
Okay. That's that.
I see. Okay.
Okay. Now, type one, case two is, if I know where the picture is, I think it's this one here. No, it's this one here. Okay, this is case two. Okay, so look at what's happening here. In this case, we start off always from true, and we are deriving certain results. You see what I'm saying?
I see.
Okay, so what I did in NKS here was I said, there is a negation operation.
Okay.
These strings have a negation operation, like it could be inverting, black and white. And then what I asked was, given that idea, you can then have a notion of completeness versus consistency. Okay?
Yeah.
So, does it overrun? Does it not overrun?
Exactly.
Okay.
Yeah.
So now explain to me, because I don't understand it. Okay, so I think we understand these two cases where this is starting from true. Both of these are you just apply the rules, right? In a very straightforward, it is pure structural substitution, right?
Yes.
Okay, so now explain to me the type theory version of this one. Can you do that? Because I didn't understand that at all.
Oh, okay. Well, the reason why I brought up the type theory is because the initial condition is true.
Yeah.
Right? Okay, so at least in HOTT type theory, right? True is just, whatever your type is maps to one. Okay, but one is just this type that's uniquely inhabited. And if it's false, maps to zero, and zero is this empty type. And an empty type doesn't have any constructors.
All right, okay. So type theory analog is we start from the always inhabited type.
You could look at it that way. If you treat it as your initial object, basically.
Right. From the always inhabited type, quotes one, so to speak.
Right.
And then what we're doing is we're saying, how can we make type constructors? Okay, then we're saying our axioms are type constructors starting with the inhabited type, right? Am I right?
The axioms are type constructors.
Yeah, kind of. Yeah.
So what will happen is we're building up symbolic expressions here, which can be thought of as type expressions, right?
Yeah.
Yeah. Okay. Right.
And then the statement that those things are inhabited is a little weird because we've turned it upside down. We'd have to invert. I guess the axioms are always two-way. Actually, the axioms. Okay.
I mean, it just to be clear, right? If you compute the thing, then it's inhabited, right? Because you've actually proved its existence by creating it. And then,
sure.
Yeah. So anything you have that you computed is in sense inhabited constructively.
Right. But now one of the things that's an issue here is normally, okay, so in the type 1 case, type 1 subcases, reversible versus not. Okay, so it is possible to have a type 1 system where the rules are not reversible. In ordinary math axioms the rules are reversible, are two-way. Does that make sense?
It's not obvious.
Are they always two? Are they always two-way?
Yes, I think so. I think so, because axioms, well, okay, equational axioms, the rules are two-way for equational axioms. Okay, so let's remind ourselves what the axioms that, boy, there's a lot of useful stuff in the NKS book.
Well,
okay,
you should write a thank you letter to whoever wrote it.
Okay, so let's look at these. Okay, so some of these are clearly equational, right?
Sure, yeah.
But some are not. And how do we think about?
Aha, yes. Okay. It's a good
How do we
question.
think about the non-equational ones? Right. I mean, some of these are equational. So let's take this example of Robinson arithmetic. Okay.
Mm-hmm.
So some of those are not equational axioms. And for example, 0 is not equal to successor of A. There's no particularly useful other way round version of that. I mean, in other words, it's, if I say A plus 0 equals A, I can clearly generate things by starting with A, going to A plus 0, starting with A plus 0, going to A. Right? I can trivially turn that into a pattern.
Okay.
Whereas I have no idea how to turn into a pattern into a substitution. 0 is not equal to successor of A.
Well, right. This is the trouble that we've encountered as well.
Well, okay, so fine, but so this is really for math. For math, this is primarily about equational axioms, which means it's like, compare universal algebra. That's the kind of thing it's dealing with, right? That's a certain area of mathematics, but it is not dealing with other predicates, if I'm not mistaken. So
yeah, that's where pattern logic is required.
Which?
Like accept and alternatives and such, that gonna help to construct this kind of non-equational actions.
I see. Okay, so the claim is sort of type 1A is the axioms are not purely substitutional.
Oh, wow.
They require, they also involve except, etc. So in other words, there is meta logic, to the patterns, so to speak, i.e.
Nick, would you call those meta rules? Or were you thinking of except as a meta rule?
Well, you always can turn any pattern into equational, right? You can just, if you have just except pattern, you can also add except equal the same except.
Wait a minute. Only if you know the universal set can you turn it. Isn't that right? I mean, except. How do you deal with? I mean, except is negation.
Yeah.
Basically. So except effectively defines negation. A version of negation.
Yeah, I'm just saying that it's not necessary to have it like an additional expression for the things that we are evolving. We still can turn it into a two-way rule or this equality just by equating it to itself.
I didn't understand that. Wait a minute. What are you claiming? So, I mean, one thing that I understand is that you can, if you allow your patterns to contain except, then you can compile a wide range of mathematics-like statements into pattern transformations. I mean, that's what I was claiming. But if you don't involve accept, if you don't allow accept, then you only get the universal algebra type things. Does that make sense?
Yeah.
Does find equational proof allow inequality? Not equal to? Okay, so find equational proof allows not equal, which is like having accept. Okay, so I want to, if we're okay, so how would we do? So the question is, in this type 1 rubric, how do we deal with things like this? Can we do it or not? There are equational ones where it's trivial, right? We trivially know how to do it. But the non-equational ones, or the ones with inequalities and things, how do we do it in this kind of model where, you know, in this very structural model where you start with true and you just generate things?
Well, the first question I have is, before we even consider disequality, what's equality in type 1? That's my first question.
Equality is just, okay. No, in type 1 case 2, in type 1 case 2, there are two forms of equality. Okay, so wait a minute. Okay, there are two forms of equality.
Okay.
There is the within an expression, you know, some of its symbolic constructs could represent equality.
Okay. Yeah.
But then between expressions, there is a built-in metalogical notion of equivalence.
Right.
Okay, so here we're distinguishing within an expression, there's a notion of equality. Between expressions, there's a notion of equivalence, but we're not bringing those together, so to speak.
Right. So then the question is, can we negate those?
Well, which ones? I mean, the ones within an expression.
The second one. Yeah, the second one.
Okay, so the first one is easy to negate. Right, there's just some operation. Okay, so negation within an expression, it's just some transformation, some, you know, just some transformation on the expression represents its negation.
Okay.
That's what I did in NKS. Okay.
Okay.
NKS form. Okay. Now, between expressions, the statement you can't get there from here.
Right.
Right. So negation between expressions okay, so what that would be, okay, so how would you prove in this multi-way system? You'd have to prove that you can't get there from here.
It's pretty much undecidable.
Which is undecidable. Which I think is what right. So therefore, i.e., negation at the metalogic level is not decidable, not generally decidable.
Yeah, but you still can't do it like in practice.
What's that? You might
But
be
in
able to do
practice,
it
you
in
can do
practice. Yeah, you might very well be able to do it in practice.
Could you hold it as a null hypothesis? The null hypothesis being you can't get there from here. But if you end up being able to get there from here, then you
Then you've
basically
got inconsistency.
well, then no, then you would negate your null hypothesis. Your null hypothesis would be that you couldn't, but then you
Yeah.
prove that that null hypothesis is false. But you have
Well, that's
then
fine.
you actually have something constructible.
I see. That's fine. But I think this is okay. What we're now trying to do. So I think this is actually something I don't know whether I knew this in NKS. Maybe I did. I probably have to actually read the notes to know if I know that. This rings a vague bell that I knew this.
We spoke about the boundaries of entailment cones and this kind of thing before as well.
No, but that's not relevant to this. That's relevant. Oh, you're saying it is relevant to this. I don't think it's as relevant to this. I think that's a type 2 story.
Okay. Yeah.
Okay.
Just remembering it. Yeah, that's fine.
Right. And we probably need better names for type 1 and type 2. But this is something
okay.
that is what's that?
Yeah, well,
Otherwise,
let's see how many we have and whether or not some of them end up having common features. We can name them, give them cool names later, right? Yeah.
Unfortunately, I know enough about how science progresses that they'll end up being called type 1 and type 2.
Oh, like Rule 30.
Well, Rule 30 is fine because you can decode it. It's just it's like the classes of cellular automata, which I could have named with names, but it's actually better to name them with numbers because otherwise you throw too much, into them. Okay. All right. So in type 2, the axioms are represented in the same way as the rules. Okay, that's the critical thing there. Okay, then entailment. So then entailment is a way of applying. So then let me see. So in type 1, events are just edges. Right?
And there are a fixed number of rules in type 1.
Yes. Events are edges. There are a fixed number of rules apart from potentially optimization, right? Though there may be optimization, though in practice, there may be, quotes, DAG style optimization, shared common subexpression optimization, right? That's what lemmas are. It will be shared subexpression optimization, which corresponds to the formation of lemmas.
Would be that Knut-Bendix completion thing when you just use critical pair lemmas to just adding more lemmas?
I don't know. You have to tell me. I don't know. I mean, let me think about that. What's the relationship of this to Knuth-Bendix? Okay, I don't know. Let's come back to that. I don't understand that yet. What does Knuth-Bendix look like for strings?
Well, I know that it's like, because I'm still only understanding it currently, that the Knut-Bendix completion basically means you're doing critical pair lemmas derivation similar to what I had, right? And adding those lemmas. So when
I know that,
only,
but yeah. Look, to have Knuth-Bendix, you have to have two-way edges. That will only work if these are two-way, right? Type 1 subcase is reversible or not. If it's reversible,
but you can't have those, right? If you have in type 1, you can, if you build a path, you basically constructed a two-way expression. Then you apply your Knut-Bendix completion to this palm
wait,
that you
why
just
have you
constructed
constructed?
and make it a new lemma.
Oh, I see. I see. You're saying, I see. You're saying, yeah. Okay, so you're saying, in this case, every path can be reduced to a new quotes axiom.
Yeah.
I.e., if, X, there's a nice symbol for entails. What the heck is it? It's the wavy arrow symbol, isn't it? We better find out what the thing is. Special characters. There's a nice symbol for entails, I think, which we may not have.
I mean, besides just arrow. What?
Yeah, there's a Unicode symbol that means entails. Hold on a second.
Is it the turnstile?
No.
There's a way. I mean, I've seen the wavy arrow before, but it's usually for path in homotopic type theory. Yeah. Which of course
basically
also
means you can give right or left hand side to the right hand side with some sequence of rewritings.
Hold on a second. Oh, you're right. The turnstile is in entails, but I thought there was another one. Semantically versus syntactically. Okay, so let's see. What do we call this? So that one there, I hate that. I absolutely hate that. This is, I hate that symbol. I mean, let's not use that symbol.
Stephen, is it this? I just put it in the chat.
Arrow.
Is it that thing?
Yes, it's that thing.
Okay, I just searched,
Yeah, okay.
wavy
so,
arrow. Yeah.
So X.
Great.
Okay, I wonder what that parses to. I think it's a letter-like form.
Yeah, just Unicode.
Okay. All right, so I think we should use that for entailment.
Oh, okay.
Yeah, go ahead.
One other question about type 1. All the axioms are given ab initio. They're there at the beginning, right? They're not added.
Well, this is a case
on.
where we're adding them. This is where we're adding them. The axioms in type 1 are pure entailment axioms. They're pattern entailments.
Yes.
Okay. So
Yes.
if we're dealing with strings, for example, a pattern entailment is the same as an ordinary entailment.
Yes.
Okay, so that means that as soon as we derive string 1 goes to string 2, we can add that as a shortcut. You see what I'm saying?
Okay. Right. So we have that thereafter. We can use that.
Well, we can choose to use that, right? We can choose to use that thing. So that's we start with, okay, so this is a different model, except when we add already proved lemmas.
And those aren't there to begin with. Basically.
No, that's right.
Okay.
That's right.
They're not presumed to be true or anything because we haven't actually witnessed them.
That's correct.
Okay.
That's correct. So
I like that. Yeah.
Right. So they're generated, and notice the important point that there's nothing that needs to be two-way about this.
Yeah. That's why Jonathan's multi-way system cannot by index completion. Given a set of rules, it just generates more of them by doing some kind of this normal forms, critical pair lemma stuff.
Okay. Well, I mean, I think that what that must be doing, see, it's not true that things that branch in a different direction here, right? If it isn't two-way, there's no guarantee that the things that you generate are equal.
Right.
So I'm saying if it is two-way, then they're equal, but otherwise it's not clear.
Mm-hmm.
Right?
You can only generate one-way rules.
Yes, which means you can't use critical pair lemmas, I think, unless I'm very confused. I think critical pair lemmas.
Critical pair lemmas are for rules, just for one-way rules.
How can that be? I mean, okay, so let's look at that. Okay, so critical pair lemmas. Okay, so let's say we have A goes to, let's say O goes to A, O goes to B. Okay, what lemma can we deduce, or where that arrow is really an entailment arrow? Right, what can we deduce from that? We cannot deduce that A goes to B. On the other hand, if we know that O is equal to A, let's say two-way rule A, O two-way rule B, then this implies, A two-way rule B. Right, we can deduce.
I think the point of critical pair lemmas, if you have those one-way rules above, you still derive A goes to B. You can derive it.
How?
Or
How?
You just postulate it. That's the Koenig's completion, I think.
Okay, let's understand how that works, because I don't understand that.
Even if you just use my code for critical pair lemmas, which is just a typical implementation just from the definition of it.
Okay, well, let's understand. Yeah.
Just two rules, it's gonna make A goes to B.
Okay, hold on. So where is that code?
Well, it's in functional repository, not ready, two-way multi-replace.
Okay.
Right? Even without patterns inside, I think it still would work.
Multi-replace or two-way multi-way system?
Oh, that's not mine. Two-way multi-replace.
Oh yeah. Okay. This is your crazy thing, which has all possible research in it.
Yeah.
Derived by following all possible multi-way paths. And thereby making an absolutely huge expression, notebook. Okay. So now, critical pair lemmas. Should I take this code out and just use it? Can I use this? Is it self-contained?
Yeah, I think.
Looks
well,
like
it uses one more function above, I think. Select positions. And then that's it. Oh yeah, I actually tested it and it's not deriving it. So maybe I was wrong.
Oh, pretty patterns. What's pretty patterns? Well, I think I need this too. Okay. So now what is this going to do? So what do I do to run critical pairs? Can I do it? Can I do it on lists or something? Can I say?
Well, just two rules. It's just critical pair lemmas requires two rules. One-way rules.
Okay, but let's do literals. Rules with literals. Can I do that?
Yeah, I guess. Just, I think that's gonna work. exactly like that, because it has to match. So it has to find a subterm in the first left-hand side, so that the second left-hand side matches against. So C, D should match somewhere inside of AB.
Help me
So
out. What is the minimal case of this?
So maybe try to turn A, B into patterns so that C and D can unify there. I think that's
okay. So let's do this. So let's say f of A, f of B, for example. Okay.
Yeah. Those A should be also patterns then.
What's that?
Then everything should be patterns, like all those A's and B's.
But they can't be with one-way rules.
No, that's how my implementation would work. It will turn them on to, yeah.
Okay. So this is like G of C blank, G of D blank. Okay, I am so unbelievably confused. Okay, what's happened here?
So you need, so what happened there? So I think you need to like the last rule, right? Oh no, whatever, pick any of those, like the first one. Just take first of those, or ignore it. This means that there is a first position and subterm A that matched, right? So the first substitution, the first critical polylemma matched A against C and D.
I am totally confused. So the basic point is that in the case where subterms can match, somewhere I discussed how Knuth-Bendix works for strings. Where is that? Is that recent or is that?
In the context of the physics project?
Well, I'm not sure. Let me look it up. It's either in NKS. My gosh. You know what's really upsetting about that? That is definitely spaced by 20 years in my life. And I can't remember when it was. Okay, here we go.
Oh wow. Oh, okay. Well, I wouldn't have been surprised if you had told me it was a paper from last year.
Okay, let's just read what this was. Okay, given a string P which gets transformed either to Q or R by the original rules, I can always imagine adding a rule QR or RQ that makes the paths, so this is about confluence, that makes the paths from P immediately converge. To do this explicitly for all possible P that can occur would, however, entail involving infinitely many rules. To just additively add new rules for each so-called critical pair that is obtained from strings P that represent minimal overlaps in the left-hand sides of the rules. Right, because you have to have this notion of minimal overlaps, and that's where you have the ordering.
Yeah. So we picked the one-way rules so that you always reduce the size of your term. You reduce the string in size. Something like that.
Okay. Okay, so this is unfailing completion, which is what find equational proof uses. All right, that was this one. I think I remember the other place it showed up. Yes, this is where it showed up.
That's pretty vague.
No, but there was a less vague piece. I remember there was a less vague thing. For the rule, okay, so this is an example. For this rule, minimal additions to achieve causal invariance are those. You see, here's the thing that's bothering me. What's the relationship between... Yeah. This is the point. Look, this is the point.
Mhm.
Given a one-way rule, okay, it's all well and good. If we go back up here. Well, there we go. It's all well and good to say that we can add something which makes them reconverge, but that doesn't mean that the two things on either side of those branches are the same. They only would be the same if you had two-way rules. With two-way rules, they're always the same. Any two things that branch from one thing are always equal. That's a feature of two-way rules.
Okay.
But with one-way rules, you can... Oh, I see the point.
That's why
Is that what univalence basically says? That if the things map to the same thing, then they are the same.
I mean, not quite, but it's in the same spirit, I think. What you're
right. But I
what
mean,
you're getting
the
at.
thing is, do you see what I'm saying? That here, if I look at this thing, AB, whatever it is, and AB there, those come from different branches, right?
Yes.
Yep.
Yes.
But nevertheless, as a result of this completion, they converge.
Yes.
Right. But then the question is, are these two things considered equal? Because normally, by considered equal, we mean they are time-like separated from each other.
Yeah, usually.
Right. So normally,
yes. Yeah, I understand. Yeah.
Normally, equality is time-like separation.
Time-like separated equality. Right.
But this is, in like Jonathan's interpretation of quantum mechanics, the whole idea is, what's that?
Branch-like separated equality.
Right.
Say that again?
Branch-like separated equality.
Yeah.
Right.
Branchial equality. Yeah. Right.
Right. It's time-like separation, but well, what it is that you can, completional equality is time-like separation, but you can have branch-like separated things which converge, and you can consider that a form of equality, potentially.
Do they have to be converged? Okay. There's the completion, but then is it also a necessary condition that they both originated from that same single?
Well, that's just the nature. No, they don't have to have originated from the same thing. That's just a case in which.
Okay.
No, if you take a branchial graph, if they're connected in a branchial graph, they basically say that they're equal in this way.
Right. So enforcing all critical pairs is like compressing the branch hill graph.
Yep.
For all
Transitive completion. Make a transitive complete branch hill graph and add all the edges to your rules.
Yeah. I like the sound of that. A transitively complete branch hill graph.
Right. Enforcing all critical pairs like compressing the branch hill graph by transitive completion, by transitive closure, basically.
Transitive closure.
So that's like saying the observer.
Oh gosh, the observer hasn't even made an appearance so far in this discussion.
Yeah, but the observer is about to make an appearance.
Okay.
Because in fact, this is an interesting model for the observer. Look. Okay, let's go to a different place here where we are going.
How far back in time are we going? 20 years or one?
No, we're going about a few weeks.
Goody. Okay.
Just for once. Okay, we're going to make.
Oh, from the live stream.
Well, that was a live stream about observer theory, but we're going to go. I actually need to move the other notebooks that I had, which I had somewhere else.
Mm-hmm.
Observer theory 04. Okay, so now the claim is. Oh, this is kind of interesting. So consider an observer operating on a branch hill graph.
Mm. Yeah.
The branch hill graph already defines equivalences. You see, the branch hill graph is already defining. Oh, yeah. Look. Ancestral closeness. Yes. Look. Okay. Yeah. Observer operating, coarse graining a generic graph.
Okay.
So let's make a graph. Let's have a slightly complicated graph. Let's make a I don't know. Let's say graph data of 40. Oh, for goodness sake.
Fullerene.
Graph data of take that, 5. Oh no, that's because I did that. Oh, this is so, okay. All right. Let's take one of these graphs, slightly non-trivial graph like that one. Okay.
Mm-hmm.
And then let's ask the question, what is an observer? So I'm claiming that if an observer simply takes, I'm just going to actually, just for fun, I just want to see something here. If I just go 100 here, I wonder what I'll get. All right, I don't know which of these are interesting, but yeah, well, okay, so there are graphs with various kinds of structure. Okay, so
I just didn't know that the graph data had this capability.
What's that?
I just didn't know that you can extract from the graph data some interesting graphs, just giving a number of vertices. Never used that.
See what graphs it has that are sized to. Oh, these are boring. Well, that might be interesting. I don't know. These are just not very. We need graphs that have sort of pseudo-manifold structure to be interesting.
Yeah. Wolfram Physics.
Indeed, a very good source, an excellent source. And I'm afraid that's where we're going to go. Let me just find one. It's kind of amusing that that's where we have to go. Let's see. I need one that is a pure graph for what I'm about to do. Those are all.
You can turn any hypergraph into a graph anyway.
Yeah, I know. Okay, all right, fine. We'll do that. Okay, all right, fine. Let's do that. Let's take that strange object. Okay, how do we make that? Let's see, we take final state, and then what do we do? Graph. I've forgotten how to do this. Graph from hypergraph, right? Is that what it's called?
Graph to graph. Hypergraph to graph.
Yeah. To graph, yeah.
Probably don't actually need to. Let's actually not run it for 2000 steps. Let's run it for like 500 steps. Okay, great.
Okay, so you were saying about observers.
Right. So the point here is that I claim that an observer coarse grains this graph. What does it mean to coarse grain that graph? Okay, I think it means, for example, okay, what is coarse graining on a graph? So does it mean that every neighborhood of a node turns into a single node? The question is how to do that consistently.
Right.
You kind of want to fuzz this graph out. How do you do that?
Now wait, before we answer this question, Stephen, you were saying, aha, oh, aha. I mean, was it this question or was there some other?
Yes, it's this. The point is that what I've been looking for is a general way to think about, well, I don't know, is transitive closure, okay, is there a way to do this? Okay, it could be, how do you do like one-way transitive closure? That is one-step transitive closure. That is every node, we want to connect both to its, it's like the square of the graph. It's like squaring the adjacency matrix. One case, connect every node directly to its two-step as well as one-step neighbors.
Oh.
Right? That might be a way to do it. So we can do that.
Oh, yeah.
We could do that by squaring the adjacency matrix, if I'm not mistaken. Is there another way to do it?
Well, you want to try it?
I don't think so. Well, I don't know.
So can you change the matrix and then get the graph back?
Yeah,
from the new matrix.
Okay. We just take the adjacency matrix and
so there's a graph power. Is it doing the same thing?
I bet that's the same thing.
Nice.
Okay, let's see if we understand that. So let's say cycle graph of 10. Okay, so now, except I really want directed edges here. I don't know whether we can do that for this. Oh, yeah, we can. Oh, nice. Graph power of this Okay, so what should that do? Comma 2, look at that. Isn't that magnificent? Right?
Okay. This is coarse graining.
It is coarse graining. Yeah.
Wow. This is interesting. Well, let's see what it looks like on this more elaborate graph.
Right, but I mean, the question of how we think about coarse graining, then what do we do once we have this? This is related to what that chap Niels Bass was talking about, except he didn't get very far with it, of trying to have a a formalism for hierarchically defined graphs. So I'm saying, and what the coarse graining would need, you turn this graph into the hierarchical graph. In which a group of nodes have a sort of bundle connection to another group of nodes, right? So you equivalence a bunch of these nodes together, and then you equivalence this is the way to do it. Okay, let's just do the graph power of this. Okay, it's going to have a lot of extra edges. A lot of extra edges. Okay, there we go. All right. So now what we're going to do is we're going to ask the question, how can you equivalence together? You want clusters of these nodes. See here, we could just combine two nodes. Okay, so here's another possibility to coarse grain. We just pull in things along an edge. Right, so we combine those two nodes.
It's transitive reduced then. It's gonna be right? Reduction.
Is it? No, I don't think so. I think it's a different operation. And the problem is it's not obvious you can do that consistently everywhere. Okay, how do we do that with a graph? What we do is we replace. How do we do that? We say, we just equate two nodes. Yeah, it's the most equate two nodes. Okay, so given a graph, let's say this graph here, how do we equate the nodes? What we want to do, go ahead.
The naive way would be like take a list of edges and map
I understand.
over it, and then make vertex replace, right? Left to the right.
Well, I think all we have to do is say edge list of this. Mm-hmm. And then all we need to do is slash dot 5 arrow, 7 or something, 5 arrow, well, something that's connected to 5 arrow 6. Right? And then we have to say graph of that.
Basically, turn an edge into a loop.
In that particular case, it does, because it just makes, but if we had a grid graph, see, it does that.
Right.
Right, it's going to have a self loop there. Just, it's tying everything in a bow, so to speak.
But do you actually want to kind of contract that loop down to that point?
Yes.
Yes. Okay.
Yeah, but this is just the indicator that has been
pinched
reduced.
Off. Yeah, right.
So notice this is actually rather similar to what we're doing with the axioms. That is, we're applying an edge to the graph. We're taking the graph and we're compressing by an edge. You see what I'm saying? So in this case, let's take the example here. Let's take this as an edge list, and let's say rule that. Okay. So now what we're going to do is we're going to say to this, we're going to say this slash dot random sample of that comma 5. Okay, and then we're going to turn that back into a graph. Okay, that's what's going to happen. This is actually kind of nice. Okay, so then here's what we do. So we say random, we say graph random reduce of the graph, and then the number of things we're reducing. And so all it is,
random sample.
yeah, I know, but I need to do it with. I say graph of R slash dot random sample of R comma N.
One more.
Okay, so now if I say graph random reduce of grid, let's say 15, 15, comma 30. Oh, grid graph.
Yeah.
Hey, this is cool. This is really, this reminds me of, you know, when you do meshing.
Yeah.
So if we went
Maybe-
on, go ahead.
Maybe also remove the loops.
Yeah,
Eliminate
let's
loops.
not worry. I don't care. The loops are fine. You know, it's like
Interesting.
simple case
Yeah.
is merging of triangles in meshing or triangulation. But this is the more general case where we're merging neighboring graph things. So what this is saying is, one thing the observer could do
Right.
is to make a whole bunch of local mergings. But what's interesting is the observer, let's just see what happens. I'm just curious what happens to this thing as it goes.
Coarse. Yeah. Increasingly coarse. Oh. Yeah.
100, let's see, what's 15 squared? I don't know what 15 squared is. In steps of 100. Oh, that's as many as happen. Okay, let's do 50 then.
You can just nest it.
Yes, that's a good idea. I agree. Okay, so let's say nest list, graph random reduce, hash. I don't quite understand why it didn't go further than that. So I'm saying, because eventually it should, well, let's just see what happens. Yeah, I see. I think if we nest it, it will actually go further. Well, let's go 50 then. I don't know how many to do.
Well, maybe that's the loops. You also like each sampling can also reduce loop again, then it does nothing. So with each iteration, it reduces less and less.
You mean we should remove the loops?
Yeah, because the more loops there are, the more probability to pick the loop and contract it again.
Okay, how do we remove the self loops? Isn't there a function to remove self loops? Well, we could just remove
simple graph. Simple graph.
Oh yeah, that's right.
Maybe I should try up to
I
instead of 50.
know.
Yeah. It should be in the graph, in the definition, so that n should always be less than number of edges. Or it should, yeah, basically. Oh, no, not up to n. Or does it work? I'm not sure.
Think so. I think that will work. Well, that might have gone into some weird loop, but let's just say 10 steps here. Yeah, that worked. Fascinating. So this is an observer. What's that? This is an observer basically trying to observe that grid and conflating certain pieces of the grid.
Yeah. Yeah. But the question is, how does the observer do it?
Well, the observer can just follow. I think the observer, okay, so I think the observer is more following space-time paths.
Well,
rather than, yeah, go ahead.
Before we did this, and you were saying, aha, oh, wait, you were discussing, shared ancestry. This is what we were discussing right before.
I know that, but we didn't need, I realized we don't even need shared ancestry. This is already a thing.
You sure the coarse graining doesn't follow that in any way, right?
Oh, I see. Well, yes. Okay, fair enough.
That's why I'm bringing that up.
Fair enough. Okay. So another form of coarse graining. Backtrack to ancestry.
We can do something like this.
Or forward track.
Yeah, right.
Well, or forward track to confluence, to merging.
Right.
Because that's what allows the coarse graining to be consistent, is that it will eventually merge.
Right. So should we take an example of a graph and apply this coarse graining, but according to ancestry backtracking or confluent
but we need
tracking?
it's more complicated, because what we got to do is, I mean, what's really interesting at a meta level about this, hold on a second, allows coarse graining to be consistent. What's really interesting is that we keep on being led back to, our full kind of Wolfram model rules. Because basically you can't do this. The thing we're about to do is going to need a notion of multi-way graphs and a notion of space and a notion of time.
Mm-hmm.
It's going to need branch hill space and time. Now, or I suppose we might be able to get away with pure branch hill space.
Maybe we should start with that.
Yeah, except we have less intuition about that.
Wow.
Because that's quantum observation, as opposed to statistical mechanics, where we're doing it across space. But so in the branch hill case, yeah, okay, so the branch hill case, can either coarse grain by fiat conflating different paths at a particular step, at a particular time slice, or we could potentially do it or by taking time bins. See, but again, okay, time bins and saying things are equivalent if they evolve into each other over a certain time. But to make this meaningful, we need to project to branch Hill space, to a consistent branch Hill space, to a consistent, somewhat time-independent branch Hill space. Does that make sense? Okay, so the point is we're trying to get equivalences, right? And we're saying that we can say these, remember, the problem is the river is flowing. Old Heraclitus.
Dang it, yes. Okay, you beat me to it.
Heraclitus was right. The no cloning theorem of quantum mechanics is what Heraclitus figured out. That is, you can't go in the same river twice. You know, you can't step in the same river twice. Right. I think that is the no cloning theorem, basically, because it says that in the multi-way graph.
You should tell Hatem about that. Yeah. Right.
Yeah. I mean, so that, and the reason, okay, so given that fact, it doesn't do one any good to do the time course graining, because it's still the case that the things in different places in branch Hill space are different.
Fair enough.
Okay, and the only way you can make them the same is by some kind of, projection in which you say it's moving around in branch Hill space, but we're associating the things at one time step with the things at another time step. Do you know what I'm saying?
Yeah.
So the time evolution is moving us around, and we could do the same thing here. I mean, we could apply graph transformation rules to this.
Sure.
Right. And what we're saying is, apply graph transformation rules, and say that nodes that evolve into each other, quotes each other, after n steps are equivalent. Now, when I say into each other, old Heraclitus, pokes his head up and says, but you can't, they're different, right? The river has changed.
Yes.
It's so fascinating that so many of these philosophical things are actually sort of correct. It's very fascinating to me, at least. It is not a good advertisement for science.
Well, unless you view them as engaging in primordial science, in which case, then that's fine. Then some of the primordia are still useful. There's also plenty of rubbish, Yeah,
sure. Yeah, right. But actually, what's interesting is in my, hierarchy of paradigms, most of those people were in the kind of structural paradigm.
Well, yes, they certainly weren't in the multi-computational paradigm.
Well, for sure, but they also weren't even in the mathematical paradigm.
Right.
And Heraclitus was unusual in that respect because he did think about time in some sense. Anyway, we'll get to that when we start doing this philosophy mapping.
Okay. Let's keep going.
So this is actually quite useful. I mean, this is kind of gives him a bit of a framework for thinking about this observer theory thing, thinking about what it means to it's sort of a principled way. Yeah, I mean, what this is doing is saying within the system, because you could say, let's coarse grain completely outside the system.
What?
This is saying coarse graining from within the system. You are embedded in the system. How can you coarse grain?
I don't even know how you would coarse grain from outside.
Oh, it's easy. I mean, it's like what you do, I don't know, when you make a JPEG image and you take only the low Fourier components. See what I'm
Well,
saying?
no, but I mean in something like a model with an observer, what would it mean to coarse grain from the outside? You're in
It just
whatever.
means that
You're
the
a part of
observer,
whatever.
okay,
This is
but
like
no,
Wheeler's participatory principle. You're inside.
no, but I understand that. I understand your insight. But one of the things that we're saying is the whole point is it's all about what we believe. We believe at this very moment, all three of us believe that there's a definite thread of experience, that we're having a definite thread of experience. Right? Unfortunately, it probably isn't true. What is in fact true is that we're all branching, ridiculous number of times per second. But all those branches, like a critical pair lemma, we are viewing those branches as equivalent. Right? From inside the system, the only choice you have is to view those branches as equivalent, I claim. Otherwise, you have no consistent idea of what's happening in the world. Now, the question is it consistent to view those branches as conflated? Right? And that's causal invariance.
Oh, okay. Yeah.
That causal invariance means it will be consistent to do that. If it was not, if there wasn't causal invariance, you would be confused because something would have happened. Okay, the point is, in one branch the cat is alive and one branch the cat is dead. Okay. And in the absence of, that piece of causal invariance may take a very long time to resolve. The claim is that most things are very short-lived. Most of the non-convergences are very short-lived. Most branches will reconverge quickly. And therefore, when we think definite things happen, we won't be confused by that. Because we'll be able to say, yes, it was really true those branches were equivalent.
I think the meta-mathematical analog of that is interesting. Worth considering.
Well, the meta-mathematical analog of that is, I think it's the belief that only theorems matter and proofs do not.
You mean because the proofs can differ in some way, but that doesn't really matter.
Yeah, but I mean, in the type 1 model of meta-mathematics, that will be what we would say.
Okay.
The mathematician is conflating all proof paths.
Mm-hmm.
Let's see. It is a little weird.
But this is where, Stephen, just to recall, this is where you described this before as the mathematical version of quantum mechanics or even quantum effects, right? Where midway, the paths might differ. They might differ in some way.
Yep.
Oh, no, sorry. This was destructive interference.
No, destructive interference
right.
is when they're actually inconsistent.
Right.
But the very fact
midway.
that there are multiple paths, right?
Right.
That you're not conflating the paths. It is, can you observe the fact? What experiment can you do? Okay, so this is, quantum mathematics, basically.
Mm-hmm.
What experiment can you do that will detect multiple proof paths in a type 1 metamathematics.
That's why you asked maths to like add quantum switch to our framework.
What? Which?
The quantum switch
To which framework?
to the quantum framework we have.
Oh, what does the quantum switch do again?
It's like you have a superposition of order of operators. So it's like AB or BA, and you have a superposition of that.
Oh, that's interesting.
Seems
Yeah, because
relevant. Yeah.
it does seem relevant. Okay. Okay, so what experiment can you do that will detect multiple proof paths? So normally, if all you saw was a textbook, let's see, how can you detect that? What does the mathematical observer see? The real question is, what does a mathematical observer see? And one possibility is they only see textbook statements, no proofs. You know, that's one possibility of what.
Why don't they see proofs?
Well, I mean, I don't know. That's just the.
I mean, because they're.
No, I understand, but
okay.
I'm saying that what we're trying to represent here is we, like old Alan, are trying to represent what a mathematician does.
Yes.
Right?
Yes.
And, old Alan could have decided that mathematicians, his computers, did all kinds of crazy stuff, but he took a very minimal model of it.
Mm-hmm.
So for our purposes, most of mathematics is concerned with theorems and not, most of the time you quote a theorem. You don't quote the proof.
You don't quote the proof. Yeah. Sure. That's fine.
Okay. So,
right. Especially
okay. So here's the issue. Normally, okay. So classical mathematics. Oh yeah, this is nice. Classical mathematics is a path, is a single path from theorem to theorem. Okay, but each one of those, what's really happening is that there's a path integral, so to speak. I think the issue is, if we knew what metamathematical space was like, then we could introduce something like a quantum phase.
Well, but that's what we're doing. That's
hold on a second. So what's happening is, if there's only one path from theorem to theorem to theorem, there's only one proof.
Yes.
You can kind of cut it at any point and just keep going.
What do you mean you can cut it?
Well, look. This is the analog. This is the analog of quantum measurement. Okay. Concluding that the thing you got from a proof is a theorem you're keeping is the analog of quantum measurement. In other words, you've got all these theorems, all these proof paths bubbling around.
Right.
And at some point you say, I've got a result, and that's the one I want to keep.
Mm-hmm.
And there may be intermediate stages of those proofs that for sort of Heraclitan reasons you can't go back to. Again, I think it's going to depend on, and I think there's going to be some bizarre relationship between unitarity and quantum mechanics and this two-way proofs business.
Right.
Just 1 second, I'll be right back.
And we can add fuzzy logic. We can't even have logic for patterns, but you have to have a fuzzy logic in order to destructively interfere patterns with each other.
Really?
Oh yeah, it's like except destructively. Well, except of something is like and something, right? That's just usual classic logic. But you have to have some fuzzy logic in order to have something like quantum phase. I wonder, like, how would language would look like if you had fuzzy logic for patterns. Then maybe that's how you do actual multi-computation in the Wolfram language, when you have patterns that are fuzzy.
That sounds interesting. To be honest, Nick, usually I only hear people employ fuzzy logic when they don't have a very good they have some bad AI, and they're justifying it by saying that they're using fuzzy logic. But this actually seems like maybe a good use of it.
It's not just the word that I made. It's actual logic, right?
No, I know. That's what I mean. I mean, I'm sure it has actually some good use cases. I'm biased in the sense that often it's like people. Oh, okay. No. Welcome back. Hey, so just for a review, there are kind of three active developments at play here, right? First was we had these different types with these different cases.
I know we haven't gotten through type 2.
Right, we didn't get to type 2, and then also there's this great observer theory progress that we've been made, and it'd be interesting to see it applied to the branch hill case. And then we also have this quantum mathematics. I mean, you know that, but I just thought I'd address the fact that we have.
Oh, okay, let's just think 1 more minute about quantum mathematics. And I'm going to go back to type 2, then we wrap.
Okay.
Okay, so quantum mathematics. I think the issue is. Go ahead.
I was gonna say that we're talking about that maybe adding phase to the patterns is like adding and make those fuzzy logic is actually what's required to make multi-computational Wolfram language in the end. That's like.
I understand your claim. That's an interesting claim. I mean, so, what is the relation of fuzzy logic to quantum mathematics? Gosh, if that ends up having a an application, I don't actually know the formalism of fuzzy logic.
That's what I was saying too. Like I hear it used often, maybe even meretriciously used, but I've never really actually worked with it.
Yeah,
I think it's rather vague, the formalism. I don't know that it actually has an axiom system, for example.
There's some continuous functions that they use, just like sigmoid functions, I guess. So that you have like continuous probabilities, not just true and false. But whether it's related to the quantum probabilities in some way,
Yeah, right.
unclear to me.
Oh, that's interesting.
Well, okay.
They use a logistic function. Oh, that's interesting.
Right.
Anyway.
So
Anyway.
So the point there is that yeah, what this is doing, this is effectively assuming a continuous branchial space, I think. That's what fuzzy logic is doing. It's think about branchial space. It's just saying there are, I mean, it's the same thing we could do for observer theory over here. We just say there's a Gaussian region in branchial space. It's kind of the fuzzy logic analog. The observer convolves, sort of has a Gaussian kernel in continuous branchial space. I think that's how that would work. Okay, so
So I think so fuzzy logic is not enough on itself, like to have coherence, right?
no, that's right. It's not. It doesn't. It breaks all of that stuff. And it doesn't preserve coherent threads of history. It's just a probabilistic approximation. So, see, here's my take on the quantum mathematics thing. I think what it is, it's something like you use only the waypoint theorems and you don't use, oh, I bet I know what it is. I bet it has to do with this entailments and type 1s and type 2s and metalogics and so on. Here's my guess. My guess is once you have a theorem on a platter, you have certain kinds of combination rules that you can apply with other theorems.
Okay.
But at the stage when you're just doing the proof, the sub-pieces of the proof don't have that same property, just like in a type 1 metamathematics. The proof is that path.
Yes.
Right? Whereas the theorem is just a node on the path. And so I don't know. It's something related to that. And it's related to the way that you can combine, I mean, yeah, it's something like this. At any given moment, okay. Superposition in mathematics. You have you're combining, combining theorems versus combining pieces of paths, i.e. proofs. And I think somehow those are different. That I don't know exactly how this works. I mean, I think the concept, but I do think the concept of measurement is going to be different in the type 1 and type 2 cases.
What are I've asked this before, and we had some answer, but I'll reintroduce it again. What's the analog of virtual particles in this?
the fact that you can generate variables. I claim virtual particles are like generated variables, where you go, where you're essentially creating new atoms that weren't there before. Where you say, A and A dot A inverse is equal to the identity. You reverse that, you say the identity is A dot A inverse.
Mhm.
And then you can go off and A you do some other transformation, A inverse you do some transformation. But so in other words, what you're doing is you're saying something like one, this A dot A bar, let's say, right? That's really a pretty direct analog. And I mean, if one of those particles falls into a black hole, which we need to understand what the real analog of that is actually. But I mean, it's kind of like it goes both ways, but it creates something, and then the virtual particle can have its own interactions without just being a vacuum fluctuation and going back to the same thing again.
But in some of the types we consider, we don't have these two-way rules.
I know. So I don't know how that works.
So we don't have virtual particles?
I don't know how that works. I think it's probably more complicated. I think probably
I mean, it's something people are trying to do, right, is to develop models that don't necessarily have virtual particles.
Who's trying to do that?
Well, like Arkani Hamed with this amplituhedron.
Does it? I don't know.
Yeah.
Does it not have virtual particles?
Yeah.
Okay, I should understand that. I didn't know that was an attribute of it.
I've said this, maybe I'll mention this as Xerxes. I think that this amplituhedron would be a great summer school project for someone who understands it.
Well, I think somebody tried to do it actually, but they didn't get very far.
Oh, well.
I mean, it's like many summer school projects. The ones, there are better and worse ways to do it. Okay, 5 minutes on type 2, and then we got to go. Okay.
Okay. Oh, well, so let's, just to revisit this, we wanted to try and understand negation. That was the original motivating question for this.
I know, but we don't understand. We understand what negation is in type 1. In type 2, the axioms are represented the same way as the rules. So okay, so case 1, every proposition is an equivalence, is a statement. Okay, that's not necessarily right. Okay, but let's assume that. If that's the case, then it is self-evident that a proposition can turn into a rule. But if we look up here, that one there, 0 is not equal to successor of A. I don't know how you turn that into a rule.
Is it a rule?
So my idea, you can just look at it as just as a type 1 expression and just equate it to itself.
I doubt that will be useful. So, okay, so there's a case 2 here, which is, okay, and the entailment based on the entailment obtained from applying one proposition to another is straightforward. It's fairly straightforward, although I don't fully understand critical pairs in this context. Okay, so that's case 2. The second case is propositions aren't necessarily statements. And in that case, the entailment might be much more complicated.
Yeah, you have to like restrict your how substitution lemmas work in order to ignore some of those higher level pattern logic.
Well, what I'm saying is, yeah, but what I'm saying, look, if you have a thing that just says f of, you know, let's say it ends up being, e.g., apply f of, I don't know, blank, g of blank or something, or e of that to, you know, some other thing, g of x blank, two-way rule, f of g of, I don't know what, you know, y blank, x blank or something. See what I'm saying? But let me not put the two-way rule in there. That's confusing. Let's say to h of whatever, right? How does one of those apply to the other one? If those can be interpreted as rules. Now, isn't this where scholemization comes in?
Oh boy.
I don't think so. Well, columnization is about just creating those variables, Scholen variables, if you have existential quantifiers.
Yeah,
We
but I
don't
think
even
this is the
talk
same
about
type of thing. Look, the main question is, how does something like f of x blank, y blank, you know, apply that to, you know, g of a blank, b blank, right? How does it apply? See what I'm saying? In other words, it will be straightforward if what this said was x blank, two-way rule, y blank. We understand perfectly well how to apply that to g of a blank, b blank, right? We just don't know how to apply, you know, it's just like we don't know how to apply the statement. Okay, this statement, a plus 0 equals a, we know perfectly well how to apply that to something else.
You don't have to have a way of applying those no two-way rule statements. Because if you create just a trivial two-way rule statement out of those, they're just there that they say that you can just turn themselves into the same.
But you need to use them in proofs. Okay, how do they appear in proofs?
But you can apply other two-way rules to this statement, to either to the left-hand side and any subtheorem.
Okay, so one possibility, these are never non propositions can never be used to generate events, to be events, so to speak. Right, that would be a possible claim.
No, event can kind of have two inputs. You have a rule and what you're applying to.
Well, okay, so but they can never be used. That you have to have a two-way rule in order to seed an event.
Yeah, but you just used another two-way rule, but you can use this one just as an input into a substitution lemma or something.
Somewhere there is a list of metalogic. Somewhere there's a list of possible here we go. There's a way, there's somewhere I remember seeing a list of meta. Boy, they could get better references there, but anyway. Inference and entailment. Okay, the entailment. This is one form of entailment, right? So I think I remember seeing a table of different oh boy. Old Michael Dummett.
Did you know him?
I knew his kids. I certainly met him. Syntactic consequence. Okay. Again, we should find a list of all these different ways that people entailment of a system by its logical foundation. Okay, well, so this is, I'm sure there was a that's not useful. That's not useful. It will be very helpful, James, if you had a chance to try and find a table of different forms of entailment.
If there isn't one, should we just make one?
Well, yes.
Yeah, okay.
Sure.
Yeah, okay. What we can't find, we make.
Okay, so okay, there's one. This is claiming that there are two kinds of entailment, basically one way and two way. Thank you very much. That we knew.
What is this?
Somebody's thesis. Entailment.
How do people understand this option?
Yeah, this is a modus ponens story.
Entailing this? That sounds like something, Stephen, you would say.
Well, yeah. Types of entailment. One-way entailment.
It took humanity until the end of the 20th century to start thinking about one-way entailment. Aren't there earlier references?
Is that what the guy says? Yeah.
Well, no, but look, like in 2000, 1998, 2005. I mean,
But that's maybe just because they like referring to recent things.
well,
Paraphrase. Entailment as paraphrase.
two
In other words, yeah, two entailment as paraphrase. Negative entailment.
Wait, that's important.
list of,
We're trying to understand that.
is it a list of rules of inferences?
Oh,
Where? That's what I'm looking for. Yeah, I want a list of rules of inference.
Yeah, just list of rules of inference on
Oh.
Wikipedia.
That was the page I was. Is that Wikipedia?
Oh, it's just with the.
You can just go to the upper
It
right-hand
is.
corner if you want the actual Wikipedia.
Yeah.
Nick has a.
I like this one instead of raw Wikipedia. It looks nice.
Instead of
Okay,
what?
but
What did you call it, Nick? No,
raw
you
Wikipedia.
you can just click this little W symbol in the upper right-hand corner.
W, yeah, and read on.
Read on Wikipedia.
Okay, this is the page I was looking for. This is exactly the page I was looking for.
Nick, you just saved me some time. But this negative entailment, I mean, their example was this is a cat implies this is not a cow.
That's just bullshit.
Yeah, I mean, how
It's
could
bullshit.
how would we do that?
So rather specifically with
How we
cows and
could?
things.
I mean, it also this is a cat means it's not. You know,
God, that's just
it's not
nonsense. It's nonsense.
like I mean, the cat has a large complement. There's a lot of things that aren't cats.
Yeah, right.
You know,
Right. I mean, you could
And
say
if
this is an animal, so it's not a cow. I mean, that's just nonsense.
well, but even in that, I mean, a cat. It's not a table.
Okay,
It's not
nonsense.
Andromeda. No,
Somebody didn't understand. It's nonsense.
No,
So I
but,
think
but
there's
this is
nothing.
why this it's difficult. This idea of negation. Obviously,
Okay, here we go. Here we go. This is what I was looking for.
Okay.
I don't know. Is this just a statement of axioms associated with implication? It might be. I think this might just be a statement of the axioms of logic. Because I think what's interesting up here.
And theorems, because I think if there's just axioms, there would be much less.
Right. Allow one to infer a conclusion from a premise to create an argument. Yes, that's what we're talking about. A subderivation. Note by this is where things really go off the rails, is when the only name for something is Latin because it was last considered in the Middle Ages.
And that's a rule of excluded middle, basically.
Well, X from contradictions.
Principle of explosion.
Yeah. Not that.
Any statement can be proved from a contradiction. Right.
Right. Okay.
Stupid thing. Yeah. Okay, but so what we want to understand, again, Nick is making the contention that the only things that can be applied are two-way rules that happen to show up. And that any other object that gets produced is just inert with respect to, it is not active in some sense. The only things that are active are, so in other words, a way to think about that is the following. Imagine that we are using replace in the language.
Yeah.
And we keep on replacing things. And every so often we end up with something which can be used as food for the replace.
Right.
And most of the time we don't. Most of the time all we end up with.
So the food for the replace also can contain a rule, but just not on the outer level.
Yeah, right. Well, the non-food, you mean? So, by what I mean is, so
the food itself, yeah, the expression.
Which one are we talking about being food? I was talking about the second argument as food. See what I'm saying? I'm saying that.
It's the first argument as replace. Replace has food.
I know, but I'm saying that. Look, I'm saying, feeding a replace. Mm-hmm. I'm saying that there is a replace of. Well, actually, we could have a replace all. Let's just say a replace for now. We have an expression.
Multi-replace.
Okay, we have an expression and we have its rules, okay, or its food. Okay, that was what I was referring to, it's food. And now the claim is that in that any food that isn't a rule of some kind.
That's kind of confusing. I was thinking as a rules being fed with expression.
Okay, fine.
So that
but look, the fact is, we're generating expressions. Okay, any food that isn't like this is passed through the multi-replace, like a rock through a snake. In some sense, right? It doesn't. Nothing. What's that? Some kind of animals eat rocks. I think it's it's crocodiles. Crocodiles.
Really?
Yes.
During times of scarcity, or just for some other purpose?
No, for some other purpose, to help grind up their food, I think.
Oh, gosh.
Yeah.
Oh, I'm glad we don't have to do that. My goodness.
Okay. In any case, my point here is that in this model, type 2 model, you're just generating tons of expressions. Okay? Some of them might be usable to generate events, but others are not. Like, for example, in mathematics, and it still bothers me. Let's say you say X, you prove that X is not a prime, right? You can still use that in another proof. It's not the case that the only things you can use are, how do you use, so how do you use a statement like prime q of blah, blah, blah in another proof?
So you use it as a substitution source, right? You can replace x with whatever, with something, potentially. Depends on what is x.
Sure, but that's a replacement done by a substitution, by an equivalence. The question is, how do I use just the fact that, look, let's say that my result was prime q of f of x blank g of y blank is true. I think this is what you were saying earlier. You can always turn that into this, right?
Or just equals to itself.
Why is it equal to itself? I didn't understand that.
Well, everything is equal by itself, so we can just turn it trivially. Just the most trivial way to turn it into equational proposition, or in other words, two-way rule.
But what if it was false? I mean, false is equal to false, isn't it?
But if you were starting with the two-way rules that we're considering true, you don't have false propositions here like that.
I'm a little confused by that. I mean, but I do understand that if you have this, that's still grist for some kind of mill. You can say, if you see this, you can turn it into true. If you see true, you can turn it into this. And then you could take this apart.
Okay, yeah. Or that, yeah.
But you were considering the case in which it's false.
No, I wasn't considering that case. I was simply considering you assert that is just one of your soup of expressions, that this is true. So I think this is the way Jonathan did predicate logic in the equational theorem prover. By just saying this predicate is true.
Yeah, something like that.
Right.
Oh, but actually, I think he made it as I said it before, like just equate it to itself.
I don't understand how that works. But I mean,
or maybe like negation of itself equals this expression, and negation of itself equals true. He has something like that.
Well, I'm not sure about that, but I need to go. But I mean, but I think, okay, what we're seeing here is that in a type 2 system, we just have buckets of expressions where any naked expression immediately gets a equivalent to true. So in other words, we have, so a type 2 system. Okay, so basically, general case. Type 2 systems maintain giant vats of true propositions. And the complement of those vats, I mean, we can discuss the complement, but that's not the main thing that's going on here. That's the negation thing, but I don't think we care. Right? You could if you wanted to. So these are giant vats of true propositions. And the question is, what mathematics consists of expanding the vat? In this case, mathematics, the progress of mathematics is the expansion of the vat, of the contents of the vat. Now, we can look at the complement. We can try to identify the complement of what's in the vat, which would be the negations, which would be the false statements. Now, it could be, and so there are two cases. This is the thing. The undecidability of negation in the previous case is related to the question of, can you paint it with falseness? Okay, so the false statements are ones which we can verify are false. Okay, so there's ones we can verify are true, there's ones we can verify are false, and there's ones where we can just go off. So, we can have a fiducial false statement that if things are equivalent to that, then we know the thing is false. But there may be many things which are not equivalent to either the fiducial false statement or the because remember, in this situation, yes. Look. Basic assumption of type 2. Yeah, this is the story. Anything can have blah blah blah, two-way rule, true. Anything XXX is semantically equivalent to anything is true.
Then you can just also add except of XXX then equals to false. And then you have a negation.
Right. This is reminiscent of there's a whole business in philosophical logic of the question of when you assert something, when you say, I am a fish or something.
Yes.
Are you saying I am a fish is true?
Yes. Well, this is what the theories on the deflationary notion of truth and the disquotational notions of truth. The same thing. And that's that camp, they would say that you're not really adding anything by saying that you are a fish is true.
Right, I know, but we're not doing philosophy, we're doing computation.
No, I know, but you brought up philosophy. Hey,
I know that, but I'm trying to understand that this type 1 versus type 2 thing is actually making the cut, because I think in this type 2 case, we have to assume this. This is the fundamental assumption of type 2.
You have to assume that anything X is semantically equal to.
Right. And that then allows you, because that then, you see, this then turns into, what that implies is, this means that anything can become a rule that can be used for substitution. See what I'm saying? That's the critical thing. That it might be the case. So we've got this giant vat of expressions, okay?
Yes.
And worst case is you just say blah is true.
What do you mean worst case?
Well, you might have an expression. The law of entailment says every time you see a top level two-way rule, you can apply it. Okay?
Mhm.
Were you to fail to see that somewhere,
Right.
you can still apply the rule blah is true.
What about it? What about falsity, though?
No, you don't have to worry about that. I'm saying the vat is all of true statements.
Oh, well, then, yes.
Okay? And so the whole point is the vat of true statements.
Oh, great. Yeah.
Right.
Yeah.
So the whole point is that what's happening is the is equivalent to true is just sort of a freebie. You can add or subtract that. Okay.
Right.
The meta logic, the fundamental meta logic, the meta logic is you can add or subtract is equivalent to true everywhere.
Mhm. Yep.
And then if you are given something which is being used as food,
Yes.
then so in fact this isn't really right. The crocodile is dead. The answer is, how do you use that in there? You just say this is, you just do this. You just say that's true, and then you can use it. So I think this is the story. I think this is this gives us the kind of, so in a sense, I don't know which one this had, the disquisitional theory of truth or something.
Disquotational. Yeah.
Disquotational.
Even worse than disquisition. Yeah.
Okay.
You really never expected the disquotation, let alone the never mind. Anyway, yeah, keep going.
Okay. So anyway, that case is, what we're saying is that mathematics, as it is normally done, implicitly assumes that theory of truth. I'm just going to look up one thing, which is I had a whole note about Tarski's theory of truth in here.
By the way, apparently lithophagy, or eating rocks, allows alligators to stay underwater for longer.
Okay, fine. Lithophagy, I love it. It's very Greek. You know, it really is very useful having learned Latin and Greek, because there's so many things where, you know, random medical terms and all this kind of stuff.
Yeah.
You can immediately translate them. Why do I not discuss here the theory of truth? I remember writing that note. Oh, truth values. Here we go. This is the relevant note. Okay, we read this and then I, okay. Sorry, this is, let me just move that to the right place here. Okay, let's read this. Well, this doesn't discuss the Tarski theory of truth. Well, let's see what. Oh, this seems to be relevant, potentially. Let me just see what this says. God, this is complicated. You know, people should read these notes, and I guess I put lots of effort into them, and they're actually, they don't typically unravel if you pull the threads. I got to go to sleep, but I think we've made good progress here, because I think what we've understood is I wouldn't worry too much about the falsity. I think there are some tricks being pulled in find equational proof. We need to understand those.
Yeah. And
We're
make
getting
some
closer.
of our own.
What's that?
And make more tricks.
Well, perhaps, but I mean, look, the big thing, which I know Jonathan has been thinking about, is proof simplification. Can we take once we have, okay, so the question is, what is the geodesic path? We clearly understand that there is a shortest path in, a shortest mathematical path, right? That involves, yeah, I mean, there's clearly a shortest path. Can we find it? And in particular, is there a topological obstruction to getting to the shortest path? That's the question of whether there's a non-trivial homotopy in homotopy type theory. Do you see what I'm saying?
Oh, I was muted. I was very excitedly saying, that's right. Absolutely. Yes.
Right. So in other words, what we should be able to see here. Yeah, I mean, so let's just make a comment about proof simplification, which is related to the quantum, proof simplification. There is a geodesic proof, maybe more than one, but a theorem prover might not find it with, e.g., unfailing completion, might not find it. What does it look like to make proof-to-proof transformations? Okay, so I claim proof-to-proof transformations, they are very much like critical pair lemmas.
Oh, I imagine at this point, Xerxes and Jonathan Hatem probably have something written about this.
I suspect they do. Should ask them. Okay,
Well,
but so okay, but look.
Yeah.
What is it? Okay, this is the point. What does it look like to make proof-to-proof transformations? But we should be able to see that explicitly in these token event graphs, for example, right? We can see this. We should see this in our token event graphs. Okay.
I would look at it like just another substitution. If proof is just a tree, it's just a way of rewriting trees into other trees.
Yeah.
And it's just making other substitutions of subtrees. So,
yeah, right. But the question is, what is the homotopy? What is the homotopic structure of the token event graph? I think that's what. Because remember, the tokens are propositions.
Yeah, it's just kind of weird to call it path because it's a tree. Kind of a proof is not a path in this sense.
Well, it takes all of its initial data and generates all of its final data.
Yeah, but one step is like it's not just a path, right? Or an edge in a token graph or any graph. It's this merging.
I know. Because look, a proof takes its input axioms slash assertions or whatever, and generates its output result, which is the theorem. That's what it's doing. That's all it is. It's just that unlike the type 1 case, where it was just like, the proof is this thing which takes axioms in and produces the result.
Yeah, I think that's the difference between like type 1 and type 2. Type 1 is just when your rules are fixed and then your proof is just actually a path.
I know it's a path, right? So in this case, i.e., in type 2, a proof is a passed light cone, a passed entailment cone.
Great.
For a given proposition. That's what it is. In fact, we should make that statement up above. I agree, that's an important statement. A proof is an entailment cone. Or pieces of an entailment cone. It's actually not necessarily the whole cone. It's not necessarily the whole filled cone.
A piece of a cone.
Actually not. No, all it is it is a path, actually not the whole filled cone. Instead, it is just a way to form the output from its various inputs. That's what it is. It's going to be something just like you see.
It's a tree.
What's that?
Just a tree, evaluating a tree expression.
Yeah, okay, you're right. Right. i.e., it's a tree. Thank you. Yes, it's a tree. Right. Okay, so right, the full filled cone. Okay. The full cone is all possible proofs. That's the point. Down here, we're going to go down and talk about that. Okay, the full cone is all possible proofs. So and those proofs will include, there is a geodesic proof. It's a bit of a generalization, a geodesic tree that is the shortest tree. And you're right that that's not completely well defined because it's got multiple tentacles. Right? Is it the sum of the tentacle lengths? You know what I'm saying? Because they're different notions of shortest proof, right? There's, it could be the case that you care about how big the intermediate expressions are. There are all kinds of different criteria, not just number of steps. But that's the question. As you move around, okay, what you're doing is you're moving around the past entailment cone, and you're finding spanning trees of the past entailment cone or something like that. Is it in fact a spanning tree? Something like that. And there are multiple spanning trees of the past entailment cone.
Yes. Well, what I know is just that the proof graph is just a deduplicated tree. No way.
Oh.
Right?
I guess so.
That's what we got for MetaMath, for the MetaMath too. Because we have a tree that if you just evaluate it, you produce a theorem, but you can deduplicate all of the nodes in there. Then it's just exactly what something like proof graph. You just more inputs.
Cool. Okay. Okay, we're getting there. Right, so I see. So it's a deduplicated tree. Oh, fascinating. Okay. Well,
and it's also, I don't know how to code this procedure because like MetaMath, it also has multiple inputs. You also like decompose those inputs just so that you have pairs of them on the end positions. So you do it, not replace all, but just a sequence of it.
yeah, I get it. It's a replace, a nest list of replace rather than replace all. In other words, it has no space-like, there's no spatial simultaneity. Right? You're saying in...
But you can as well add it because it's kind of...
In MetaMath, there are no parallel replacements.
In MetaMath, there is parallel. In the MetaMath, there is parallel replacements in the sense that the tree has multiple inputs, but proof graphs only consider one position at a time.
Okay. I got to go to sleep. This is wonderful progress. We need to continue. And Nick starts his day, I end my day. We're really making very good progress. I'm very pleased. I mean, I think we're getting close. We're getting close. I mean, the roadmap roughly is we've got these three different representations of things. We're understanding how those relate. We're understanding how to go from kind of the how you explain the fundamental model of mathematics. Then what we'll need to do is to look for particular, then we're going to do ruleology on this, and we're going to look for the homotopy structure.
That's right.
And then we want to see what human mathematics looks like and how we assess what the mathematical observer is like. And that's our roadmap.
Now, when we assess the observer, are we going to use some of these techniques that we kind of just found today?
Maybe. I don't know yet.
I mean,
I don't know what a mathematical observer is.
It's quite exciting.
Yeah, right. I don't know what
notebook.
Right. But you see, the thing is, in the end, we need to know what the fluid dynamics is like. To go from molecular dynamics to fluid dynamics, we kind of qualitatively know how coarse graining works in physics. The question is what the analog of that is in mathematics. Okay. In other words, given a microscopic ground down proof of things, the ultimate analog of mathematics is it's just a point or a line or a parabola. There are a zillion different ways to axiomatically represent it, but we mathematically just say it's a parabola.
Yeah, right. Well, we're gonna coarse grain it, and It's something to do with convolution or invariance.
We're going to coarse grain many different axiomatic representations of a parabola, all to a parabola, and I got to go to sleep. Talk to you. What we can continue this.
Yes. Oh dear. What is it? 2:49 a.m.
Yeah, right. I got to go to sleep. Okay. Bye,
night,
guys.
Okay.
Bye.
Cheerio. Good night.
Okay.
Okay. Bye, Stephen.